afternoon session. So we're very happy to have Barna Saha here. So Barna was actually a woman in theory student the first time, 2008, when we started. Then she came back 2010. So she was a student here twice. And 4 years ago, she spoke first time at Harvard. And she had such a good time, so she's coming back and so giving a talk here today. So Barna started off as a researcher at AT&T Shannon Labs, and then since then she has made a sequence of career moves and won many academic awards. So right now she's a professor at UCSD with a detour as a faculty member here at Berkeley. So without further ado, let's hear about edit this.
Okay, thank you, Lisa. Yeah, I like women in theory so much that I keep coming back, and I hopefully it will continue, and I will be here again and again in future. Okay, so today I'm going to talk about sublinear time algorithms for edit distance. So why sublinear time? Well, the data is massive. It's time consuming to access the entire data. There are maybe other computational constraints as well. Time is definitely one constraint, but the other constraints could be space. Generally, we always wanted to have fast algorithms, and in fast algorithms, linear time algorithms are generally considered as gold standard, but given the massive size of data and other computational constraints involved, we might need sublinear time. So that's one aspect, and the other aspect could be the data is complex. So you may not, even if you have your computational resources available, it may not be, you may not have access to the data. There may be other policy constraints like privacy. So you might just have only get a snapshot of data, and you have to make your inference based on the snapshot of the data. Well, as Shafi was saying, that for any theory questions, she likes to have a story. So for sublinear time algorithms, I don't know what story to tell, but let me tell you my encounter with sublinear time algorithms in real life. Okay? So I moved to, as Lisa was saying, I made a few career moves, and I moved to this beautiful city of San Diego last year, and I bought a house there. It seemed like everything was going fine. So this picture here is a picture of plumbing system in the house. Okay, so it looks very complicated, right? So when we bought the house, within 1 week, I saw there was some visual changes happening on my floor. So the floors are not looking normal, like it's like bulging up, like it was bending and things like that. I realized like, okay, so after some research, like we realized that there is some moisture sticking in somewhere. There is some water leak. And now when there is a water leak, plumbing system, right? You have to look into the plumbing system. It's a house, it's a plumbing system. It's not like massive data, but it's complicated. And you cannot really access, even if you have time, like I had all the time at that point, like my house is like floor has to be ripped up. So I wanted to spend the time to find the source of the problem, but you cannot really look into the plumbing system, even if you have all the time. It's complicated. So what you can do random, you can do sampling, right? There are few places where you can sample beneath the sink, in the toilet, or whatever, like in water heater and so on. So you have sample access to your plumbing system. And from that, you have to make an inference. And often the inference are approximate. Even the expert plumbers, they will go through rounds. And after that, they will be able to resolve the situation. So it's very much like why we need sublinear, why we had to deal with sublinear time algorithms. Like it's complicated, like data is complex. You may have, even if you have like, you only have random, we only have sample access to the data, you may need adaptive rounds. You will only get approximate view because getting exact answer could be just impossible. And there is often the algorithms that we encounter in sublinear time algorithms are randomized in nature. And there is two viewpoints, query complexity versus running time. So what is query complexity? Is the number of probes that you have to do in your data. So that's the number of queries. And the running time is obviously you have a sample, but then you have to, sample size is not the end of the world, right? With the sample size, you have to process it, and then you have to make the inference. So that's your running time. So there are two things, query complexity versus running time when you are dealing with sublinear time algorithms. It, of course, has a long history. Perhaps sublinear time algorithm was first studied under the umbrella of property testing. In property testing framework, so it was in the 90s. So in property testing, it asks the question, does your data belong to a hypothesis class or is it very far away from it? So that's property testing. So an example will be that you are given a graph G on n vertices and you want to decide if G is bipartite or G cannot be made bipartite even after removing like large and arbitrary subsets of data, maybe arbitrary subset of edges. Okay, so even if you remove epsilon fraction of all the edges, your graph will not be bipartite. So you want to distinguish between these two extreme cases. It has a very rich history starting from late 90s. Yeah, so that's property testing. Tolerant testing is more like approximation algorithms. So here you are saying, even if your data does not belong to a hypothesis class, you want to estimate the distance of your data to the hypothesis class. And you want to estimate this as well as possible, but obviously exact computation is not possible. So you are trying to know whether your data is within, is at most, the distance is at most t, or it's above some approximation factor c times t. So that's tolerant testing. It provides trade-offs with approximation factor and query complexity. Tolerant testing has also been studied for quite some time now, but it's less well understood than property testing. Sublinear time, it also appears in other settings like streaming, sketching. So in streaming, the goal is data storage, it's not running time. You want to have sublinear space and the data is coming in a streaming fashion, in an online fashion. But obviously, sublinear space is also closely connected to sublinear time. If you have a space complexity, which is, say, polylog, then obviously, like, unless you are doing exponential operations on that, you will also have sublinear time. Dynamic algorithms. In dynamic algorithms, it's not sublinear time as a whole, but you want to keep, what is dynamic algorithms? It's like your input is going through changes and you want to keep your output updated at all points. And in that case, your goal is to keep your update time sublinear. So you want sublinear update time, even though you have the space and everything to store your data. So that's dynamic algorithms. There is communication complexity where you want to have sublinear communication rather than, and those are all of these are connected in some sense. Like there are a lot of commonalities among all these models. So today we are going to look at edit distance. What is edit distance? Is a very basic measure of distance among sequences. So it computes the minimum number of character insertions, deletions, or substitutions to convert X to Y. So here you can see an example, like it's in this example, if you delete this B, then this AB, they all match. Here you can do a substitution, here you can do a substitution. And after that, you can delete this B from Y. So with this 2 deletions and 2 substitutions, so with the edit of 4, you can convert X to Y. So that's the edit distance between X and Y. It's a very fundamental measure of sequence similarity. It has a lot of applications in bioinformatics, in natural language processing, and so on. In computational biology, the main distance measure that people use is edit distance. And it's much more versatile than Hamming distance, where Hamming distance allows only for substitutions. Edit distance allows for insertion deletions as well. And that also makes it more complex. For example, in the same instance, if you had computed Hamming distance, it would have given you 12 errors compared to edit distance, because here you can just delete this A and you can match everything, but Hamming distance does not allow that. Okay, so even if there is just one deletion, that will make the 2 strings look same, but in that case, Hamming distance might have to, we'll say that the number of errors is like linear in the string size. Computing edit distance. It's the folklore algorithm is ordered in square, which you have all studied in your undergraduate algorithms class. It's one of the basic dynamic programming algorithm. So in the dynamic, you have an n-squared dynamic programming table that you are trying to fill up. You have your 2 strings, the first string on the top and the second string vertically here. And every instance here, this XY box is actually encoding the edit distance between the prefix of length X in capital X and length Y in capital Y. So this box is computing the edit distance of the prefix 0 to X here and prefix 0 to Y here. And how can you compute the edit distance here? Well, like if you know the edit distance of these 3 boxes, if you know the edit distance here, then you can just by like, so you have the edit distance for X minus 1 to Y minus 1, then you can do a, like, you just move along that same, consider the next character, like X character and the Y character. So that might be one way. Or you can delete the symbol X here and you move here, or you can delete this symbol here and you move here. Okay, so in these 2 directions, you're considering deletion, so you'll be paying a cost of 1. Here, you can, if the symbols match, you won't be paying anything. But if there is a mismatch, you are basically doing a substitution. So diagonal edges are for substitution, and this horizontal edge and vertical edges are for deletion. So whenever you have to take a horizontal or vertical edge, you have to pay 1 because you are deleting something. And during the diagonal edges, it could be either 1 or 0 based on whether the characters match or not. So what is the time complexity here? Like you are filling up an n-squared table. For filling up every box here, you have to look at 3 adjacent boxes, so constant time. So overall, it will take a quadratic time. So that's the folklore algorithm. And in fact, there is no truly subquadratic complex. If there is a truly subquadratic complexity algorithm for edit distance, this will violate the strong exponential time hypothesis. So the strong exponential time hypothesis, roughly speaking, says like if you have a satisfiability problem, whatever you can do by exhaustive search, that's the best possible. Okay, so if you assume that's to be true, then there does not exist any truly subquadratic algorithm for edit distance. Yes. It's via, yeah. So you can even think about OB, orthogonal vector conjecture as well.
Is that how the reduction is?
Exactly. It goes through OB, yes. And this is one of the pillar stone, in my opinion, in fine-grained complexity. So fine-grained complexity tries to classify problems in polynomial time, and here it's like a edit distance. It's such a basic polynomial time algorithm. It's quadratic time algorithm, and you are connecting this quadratic time algorithm with satisfiability, which was very surprising. And that's kind of one of the nicest results, in my opinion, in fine-grained complexity. So if you assume the strong exponential time hypothesis, then quadratic is the best you can do. And there is a long line of work on, but you want to do better, and there is a long line of work on approximation algorithms. So exact you cannot do better than quadratic. So what can you do in approximation, allowing approximations? And typical holy grail here is to get a near linear time algorithm. So there has been a lot of developments in the last few years. Sorry, this mask is like, yeah, so it's not comfortable at all to talk over this mask. Okay, so there has been a lot of developments in recent years on developing near linear time approximation algorithms for edit distance, and the current best is a constant factor approximation algorithm in near linear time for edit distance approximation. But here we are not going to talk about linear time, because sometimes that's generally the holy grail, but sometimes the holy grail is not fast enough. And here our favorite application is bioinformatics, because like GNS string could be really long. And even before you start a digital comparison, it may be useful to know if 2 GNS sequences are roughly similar very fast, and that requires sublinear time. Also, it might happen that there are many pairs of GNS sequences that may need to be compared. And if you know pairwise distance is somehow small, we want to compute it exactly in sublinear time. So there could be 2 situations here. One is like you have huge DNS sequences, you want to really process them fast. So that's kind of the basic intuition between sublinear time. And the other could be like you have a large database of DNS sequences, you want to do all pairwise comparisons, but obviously you won't only want to do comparisons if the distance is small. So in this kind of situation, maybe if you know the pairwise distance is small, after that you want to compute it exactly in sublinear time. Okay. So what is the model that we are going to study? So this is in the framework of tolerant testing. So we are saying that we have random access. We are given these two strings, x and y. We have two parameters, k and k prime. K is small, k prime is the big. So if your edit distance between, you are given these two strings x and y, if the edit distance between x and y is less than k, less than equal to k, you want to answer yes. Okay. And if the edit distance between x and y is greater than k prime, then you want to answer no. And in this region, in this gray region, you don't care what you answer. You can answer either yes or no. So that's the gap edit distance version, or the tolerant testing version of edit distance. So any answer allowed in the gray region, but otherwise here you always want to say yes. Here you always want to say no. And you have random access to x and y. What we are going to give is a randomized algorithm. Okay, so it's going to be a Monte Carlo randomized algorithm for this gap edit distance problem. So let's first look at Hamming distance. And Hamming distance, what would you do for this kind of gap Hamming distance problem? Well, you can just simply sample uniformly at random. So if you are trying to distinguish between k versus constant times k, then you can uniformly random sample at a rate of log n over k. Then you can apply Chernow bound, and you can distinguish between these two cases pretty easily. Okay, but for edit distance, this kind of uniform random sampling really cannot distinguish. Like there are strings where there could be two edits versus there are strings where there could be n edits, and this uniform random sampling won't be able to distinguish it. For example, like here is one example where you have two strings, everything is different, so the edit distance is n. You do random sampling, right? You sample something. Also in the random sampling, if whatever you want to do with even in the sample, if you compute the edit distance, is going to be really large, right? In the second case here, what is the edit distance? You can just delete this h and delete this g, and then everything matches, right? The edit distance is 2. But if I'm doing random samples, I'll probably sample here, sample here, sample here, and then I won't see any matches there. So the edit distance in the sample will be also large. So we are basically on the sample view, both of these strings will look same. So uniform random sampling is not going to work at all for edit distance, whereas it's for Hamming distance is just like a simple uniform random sampling. This gap edit distance has also been studied quite extensively. So it's first studied in 2003. This was the property testing framework where you want to know whether the edit distance is below k, or if not, whether the edit distance is very close to n. So that was the version that was studied in 2003. So k prime is omega n in this situation. In 2009, the proper gap edit distance version was studied, and you don't have to look into these complicated terms, but there were some results here. I will show you in a graph how these results compare. Then we had a sequence of results in 2019. We have, so this one requires k prime to be omega n. This one works well if the k prime is large, but it doesn't need to be omega n. Here it was a lot of restrictions. This restrictions was removed here, but still k prime needs to be large in order these complexity to be sublinear. In these two cases, we actually handle this one is efficient for small k. As you can see, there is a polynomial dependency on k here in the running time, and that's why this works well if k is small. Otherwise, this could be better. And then this polynomial dependency on k was not satisfactory. So the subsequent work reduced the polynomial dependency on k. That was the scenario for 2003 to 2020. So let's look into a graph like how all these results compare. So on the y-axis, we have running time, it's on the log scale. And on the x-axis, we have the value of k again in the log scale. By the way, if you look at here, the very first result is a linear time algorithm from it should be 1998. So from 1998, there is a linear time algorithm. So you can think about this as a baseline. So this does not look like a dynamic programming algorithm that I described before, because the dynamic programming algorithm would have a running time of n squared. Here you are seeing a running time of n plus k squared. So in a minute, I will tell you about this algorithm. But think about that as a baseline. So that baseline will look like this, right? Like up to square root of n. So up to k being square root of n, then you have like linear time. So that's your linear time here, k square root of n, because you have n plus k squared. Then 2003 work, which is on the property testing framework, is basically a dot here, because your k is like your, okay, so let me explain this plot once again. So here we are trying to plot gap edit distance, but what is k prime? We are taking a particular value of k prime. Here we are using k squared. So we are trying to distinguish whether edit distance is below k or it's above k squared. If it's above k squared, we know that this 2003 work requires k squared to be omega n. So k is square root of n. In this case, square root of n, you have it here. So it's like it gives you a running time of n to the 1/4. So that's your 2003 paper. Then the 2009 paper, it essentially shows you how that particular complexity will show up when you are trying to distinguish k versus k squared. But as you can see here, like if your k is more than n to the 1/3, then it gives you a sublinear time, running time. Okay, so at k equal to n to the 1/3, it goes to linear time. That was the status till 2009. Then this was our first work in 2019, where we gave sublinear time when k is strictly below n to the 1/3. So it was good for small k, but still there was these point at n to the 1/3 when it was linear. So that was 2019. And then this is this work that I'm going to describe today. This is not the state of the art. So this is 2020. So in 2020, we improved this. So now, as you can see, this is the first work, in fact, where you can get entire sublinear time algorithm for the entire region. So up to this point, you will follow this green work, like our work, and then you will follow the 2009 work. Then you can get a sublinear time for the full regime. Obviously, this is for k versus k squared, and you will see a different trade-off if it's not k squared, but something else. This is to show you that even for basic problem like edit distance, like how little we'll know, right? Like, so it's very recent work, but still this picture should tell you that this is not the complete story. That story needs to be completed. This was for k squared, but k versus k to the 1.5. If you do this, this is the plot you will get. But here, as you can see, there is a point here which is not sublinear. Like even with all these, how many colors? 4 colors, 5 colors here. Okay. So maybe we should concentrate on k versus k squared. So for k versus k squared, at least by 2020, we had a sublinear time algorithm for edit distance in the full regime. Now, after 2020, there were 2 main questions here. So why we were not getting sublinear time for the entire regime? Because of this, there was this polynomial dependency on k. So we are reducing the first term from n, we are getting n over k prime over k. But there was this polynomial dependency on k. That's why all these results were for low regime of edit distance. Okay. So there was this question, can we remove the polynomial dependency on k? And indeed, we can do that. This is a very new result of ours, which is under submission, where we can show that its polynomial dependency on k is not required, which means that for the full regime, unless like k is log n or things like that, then you will get a sublinear time algorithm. And also we can show that the bound that we get is optimal for non-adaptive algorithm. What is non-adaptive algorithm? Once again, non-adaptive is where you are doing this random sampling in one shot. Sometimes doing random sampling in one shot is not good, so you have to do a few rounds. In that case, it becomes an adaptive algorithm. Non-adaptive algorithms, as you can tell, it's less powerful than adaptive algorithms, but obviously if you can do something with non-adaptive sampling, it could be like much more practical, much easier. So that's our very recent results. I'm not going to talk about this today. And there is another work by other set of authors which appeared in Stock 2022, where, okay, so there is this other question, like the question is, we didn't have any lower bounds. So it's quite possible that for edit distance, whatever be the sample complexity for Hamming distance, that's the same bound for edit distance as well, right? So the question was, can we match the Hamming distance bound for edit distance? And this work showed that for small regime of K, that's indeed true. But they had even higher dependency of polynomial dependency on K, and they had some other terms as well. So it's not that this holds for the entire regime, but for a smaller regime of K. Okay. Okay, so with all this works, this is how the picture looks like. So let me explain this picture a little bit. You have seen these plots. This is 2003. This is, well, I was saying 2009 or 12, whatever. So this was this 2009 work. 12, I think, is the journal version. Then this was our work in 2019. This was 2020. There was some other paper which also appeared in 2020, but well, nothing to, the dependency was worse. This is the Stock 2022 paper, which is for the small distance regime. It matches Hamming distance like up to here. Up to here, it matches Hamming distance. After that, it becomes large. Okay, so if it's n is less than, k is less than n to the 1/10, n to the 0.1, then it's optimal, but after that, it's not. Our result is here. This is our recent result. So this achieves sublinear time over the full regime. And this is optimal for non-adaptive algorithms. Okay, so this is the state right now for gap edit distance. Obviously, still there are a lot of open venues here. The main question is whether you can draw this line like this for adaptive algorithms. Oh, by the way, this algorithm is adaptive. It has to be adaptive because this is your lower bound for non-adaptive algorithms. So this is adaptive, but it stops here. After that, we don't know. So whether this should go down like this. In fact, we know that this point we know is optimal. So we know this point is optimal. We know up to this point is optimal. We don't know anything in here for adaptive algorithms. For non-adaptive, we know this is optimal. So this is the overall picture for gap edit distance, K versus K squared. This is just to show you when for basic problem like edit distance, how little is known in the sublinear time regime. Okay. So let me now tell you a little bit about this result is from 2020. This is not the state of, there is a question here.
Yeah, I was just curious because the algorithm for Hamming distance was not adaptive, right? So how does the Stock 2022 results compare to the, like, is there, how is the runtime the same? Is it like a coincidence or?
Yeah, so the Stock 22 results is algorithm is an adaptive one.
Yeah.
They can match like for K versus K squared, what would be the Hamming distance? Hamming distance would be a very simple sampling algorithm, sample at a rate of 1 over K squared. Yeah. Right. So sample complexity will be n over K squared. With a lot of work, they managed to reach n over K squared with adaptive algorithm, but only for like when K is less than n to the 0.1, which is just showing that this is a harder problem. Right, and but also showing the state of the art is like for even for sublinear time algorithms for basic problems is pretty open.
Where does the into the 0.1 come from? It's change constant.
Yes, because they have these two terms, like they have n over K squared, but then they have this n to the 0.8, and they have K to the 4. Right, like you need to know where this term dominates. That's where it will match the Hamming distance bound. And if you just compare this and this, it turns out to be n to the 0.1. Okay. Yeah.
Are there better lower bounds known for K versus 2K?
There is no lower bound known, except for like we have this lower bound for non-adaptive algorithms. Yeah, but even for K times K versus constant K, we do not know whether we can do it in n over K time with adaptive algorithms. Yeah, that's the state of the art. Yes. Okay, so here we are going to learn about the K versus K square in n over K plus K square. This was the reason I chose this. First of all, like I had my slides ready for this one, and the other ones is like very recent results. I didn't have the slides ready for it. But more than that, like this is the first result which at least allowed us to get sublinear time algorithm for K versus K square in the entire regime. Okay, and this K square, in some sense, like the result previous to that had a K cube dependency. Whereas if you look at the linear time algorithm by Mishkin and Landau, it had a running time of n plus K square. So we're going into the sublinear regime, but we really do not want to pay more and more in polynomial dependency on K. So we wanted to fix that. And this algorithm kind of fixes that. So at least it doesn't blow up the polynomial dependency on K beyond K square, and it still gets a sublinear time component in the first part. Okay, so those are the two features that this result, which I thought is nice. Okay, so for that, let's start with the algorithm for Landau and Mishkin from 1998. So here we want to test whether edit distance between x and y is less than k, and the running time we are targeting is order of n plus k square. Okay, so which means like if k is less than equal to square root of n, then we will get a linear time algorithm for edit distance. Obviously, if k is large, you know that you have a lower bound from strong exponential time hypothesis, then this algorithm cannot give you anything better than quadratic. So how does the algorithm work? You are trying to fill up a dynamic programming table still, but you will be filling it up in a greedy way rather than doing the dynamic programming way. So what you do, you start with 0 here, and you try to match. This is your, if everything had matched, right? If the string x and string y were the same, then what would have happened in the dynamic programming? Like you would have just followed this main diagonal and you would have reached the lower endpoint, and your edit distance would have been 0. So that's what we will try to do. We'll try to see how far can I go with a value of 0. Okay, so you try to do that, and this is how far you can go with a value of 0. After that, you try to match this B with A, and there is a mismatch. So no matter what you do, you have to pay an edit cost there. It could be substitution, it could be insertion, it could be deletion, you do not know. But this is how far you can go with cost 0. And after that, you have to pay a cost of 1. Okay, so this means you are substituting. This means you are deleting which one? This means you are deleting here, and this means you are deleting over here. So either you are doing the deletions, or this is substitution, but you have to pay a cost of 1 here. Okay, so now you have to consider 3 diagonals, because there is a possibility of moving forward either along the main diagonal or along these 2 diagonals, right? Now we will see how far can I go with the value of 1. Okay, so this is how far we can go with the value of 1, because if you start from here, this B and B matches, then A and A matches, this B and B matches, this A and A matches, but if you try to match B with A, you get stuck. Okay, so this is how far you can go along these diagonals, and here you just have mismatch right away. You get a mismatch right away, so you cannot go much farther here. But along these 2 diagonals, you can go up to this much. So you know that in all these points, like, so at every point, we are trying to compute that for every value of I between 0 to k, we are trying to compute the farthest I valued cell on each diagonal. Can I have a value of 1 in this diagonal or in this diagonal? No, right? Because if you didn't have any edits, you will follow the main diagonal. If you have edits within plus minus 1, you will follow either this or this 2 neighboring diagonal. But if you have to travel to the diagonal on the left or diagonal on the right, the number of edits has to be at least 2. So you do not have any points of value 0 or 1 in any diagonal beyond these 3 diagonals. So after you have computed, after you have come to this point, then you know at this here, you have to pay at least 2. Then how do you get a 2 here? That you will follow 0 here, then you will come to 1 here, you will follow 1 here, then you will pay a deletion, and you will come here with a 2. So this is how far you can go in the main diagonal with a value of 2. And then you can go here with 2, with substituting here, substituting 2, or paying another insertion deletion cost. You can reach these 2 new diagonals with a value of 2. So this is how you will proceed. So this is where you get stuck with 2, then you will compute. Okay, this is where you have to start with 3. Now you have 7 diagonals to consider. And when you're considering the value of 3, you reach this point. As soon as you reach this point, you know there is a path that you have reached, and that gives you the edit distance. Okay, so this is the path if you follow. The edit distance between these 2 strings is 3. And if you follow this path, then you will get the edits as well, which is needed to compute. So what is the running time? N plus k square. So let's explain the k square first. So how many diagonals do you have to consider here? If edit distance is bounded by k, there could be at most k diagonals on the right, k diagonals on the left, and the main diagonal. So you have to consider at most 2k plus 1 diagonals, right? On these diagonals, how many times, if you think that computing these lines where everything matches takes you order of 1 time, constant time, then how many times you will get stuck? Like at most k times, right, in each of these diagonals. So there will be k breakpoints in each of these diagonals. There are 2k plus 1 such diagonals. So overall, you will be paying k square time. So that's where the k square time is coming in the running time. And now how do you compute how far, like here, what are you trying to compute? You're saying, hey, I'm starting from this A and A, how far can I go without any mismatches? This is known as longest common extension query, or in short, these are called LC queries. So what Landau and Wishkin showed in 1998, that you can do a linear preprocessing of your sequences, and you can answer these LCE queries in constant time. Okay, so that's why you have the order n time. This is for preprocessing, so that answering LC queries requires order 1 time. And then you have to ask KLC queries at most for 2k plus 1 diagonals, and that gives you the k square time. It's a very nice algorithm. Like you are still filling up a dynamic programming table, but you are filling up in a greedy way. And that helps you to bound the complexity in terms of number of edits rather than just n squared.
Why are you paying the n only once, even though there's k diagonals?
Why we are paying n only once in the pre-processing? So we are doing a pre-processing. It's done using suffix trees, okay, where you are processing the strings x and y together, and you are keeping enough information such that when you have to ask this point, like, hey, from index 3 and index 3 and 3 here, how far we can go, we can look at the pre-processed information and you can answer that, okay, I can go up to here in constant time. Okay, so that's why the pre-processing is taking care of this LC queries being done in constant time. So pre-processing requires order n time, and then it's all about LC queries. How many LC queries you are asking? So that was 1998. So in 2019, like the sublinear time algorithm, the first sublinear time algorithm that we came up with, we utilized this Landau-Wishkin algorithm, but instead of computing exact LC queries, we tried to compute approximate LC queries. Okay, so previously we were saying, if you look at here, we are asking how far can I go without any mismatch? Now we want to reduce the time complexity for this LC query somehow. And we are saying, hey, let's, instead of considering exact matches, let's consider approximate match. Let's ask this question from this point, how far can I go? Say maybe with k mismatches, okay? So that's approximate LC query. So that was our main idea at that point, like, hey, let's use the Landau-Wishkin algorithm, but now I will allow less than k, I will allow mismatches per LC query, okay? So at most k mismatches per LC query. So if I do that, now I do not get stuck over here. I can move a little bit beyond that because I'm allowing more mismatches and so on. But then I will just compute according to Landau and Wishkin. So I'm just doing same Landau and Wishkin, but I'm just allowing mismatches in the LC queries. And now I can finish it up with 2 edits instead of 3. So obviously, as you can see, like if the true edit distance was below k, here you are just underestimating, right? Because you are just moving much, you can move much farther than what you had done if you had used exact LC queries. So the yes instances will stay yes. If true edit distance was below k, you're still going to answer yes. Now the question is, if the edit distance, how much underestimation we are doing here? Okay, so how many branches, how many such green branches can be there until you reach this point? There could be at most, like, if the number of branches is more than k, you are anyway going to say no, right? You know that edit distance is more than k. So the number of branches here, even if you're considering yes instances, then there could be at most k such green segments. Okay, in each of the green segments, you are allowed to have k mismatches, at most k mismatches. So if you're following this path, then therefore the edit distance, you haven't witnessed that the edit distance between these 2 sequences cannot be more than k square. So if you're saying yes, then you know that the edit distance has to be below k square. Okay, so that handles both cases. So yes instance, yes, you are going to say yes, but if the edit distance is above k square, you are not going to say yes.
And it's to do like less than square root k mismatches per LC query, you would get k versus k to the 1.5.
Exactly. So now the question is obviously like, how can I implement these? How can I implement this approximate LC queries with few query complexity? But if you look at naive implementation, then what can happen that you have to look if which band are you looking here? You are looking at a band of 2k plus 1 diagonals, right? So overall, you are trying to fill up an area of dynamic programming which can have a size of n times k. And since you are trying, you are forgetting, like you can have up to k mismatches here. So you have to somehow sample at a rate of 1 over k, right? Like after you don't want to go beyond k mismatches, so you'll be sampling at a rate of 1 over k. But if you just pull those 2 in, then you may need to look at nk cells in the DP table. And if you are sampling at a rate of 1 over k, this will basically give you linear time, which will not help much. So the question is, how can I reduce this kind of global sampling? Like I do not want to do global sampling in this naive way, like this nk cells at a rate of 1 over k. So is there a way to reduce the amount of global sampling? So what we showed in the 2019 paper, that if you spend some local time, whenever you are getting stuck, if you look at in locality of order k around each of these LC queries, then a global sampling rate of a total global sampling of n over k is enough. Okay, so I'm not going into the details of that algorithm, but what we are doing, we are spending some local time around each LC query to overcome the global sampling of order of n, to reduce it to order of n to n over k. Then what would be the time sample complexity? Like you are spending k time per LC query. As we saw, the number of LC queries could be k square. So that's why you get a k cube time complexity over here. Okay, so you're spending order of k time. It's both query complexity and time complexity in this situation. So you're spending order of k time per LC query. But it's because you are spending order of k time, you can actually reduce the global sampling rate from n to n over k. Anyway, so that gives you n over k plus k cube time. And this k cube was not satisfactory because in Landau-Wishkin, you get k square. So like, yes, I'm reducing on the first term, but this k cube term was unsatisfactory. So the main goal of our 2020 paper was to reduce these k cube terms so that to match it the Landau-Wishkin on the second term while keeping it sublinear in the first term. So how do we do that? what do you have to do for that? Like here we are spending, we have k-square LCE queries. Per LCE query, we are spending order of k time. If somehow I can reduce the number of LCE queries to order of k, then even if I'm spending k time per LCE query, I will get k square in that term. And I will still be, suppose I'm still be having this n over k time. So our goal was to reduce the number of LCE query from k squared to order of k. So how do we did that? Like previously what we were doing, so we are still allowing approximate LCE query, okay? So previously we got stuck here, then we are initiating 3 diagonals, 1, 2, 3, and then 3 different positions. Now what we are going to do, we are going to do some synchronization. So here I'm going to say, hey, I will look at the same position y, even if I'm stuck here, I will actually move here. I'm synchronizing. Okay, so so that's what I'm going to do. I'm going to synchronize here. And I will start my LCE query from the same point in X. So I'll start my LCE queries all over here, and I will again do approximate LCE queries. But here, like, I might have different positions from where I would have started in the previous cases, the LCE queries. Here again, I'm synchronizing and I'm starting from here. It might not look useful at this moment, like, hey, yes, I'm synchronizing, but what does it give me? But anyway, so that's what we are doing. We're synchronizing in Y, and we are considering the LCE queries from that point onward, and now it matches here, and we again output whatever value we have to here. The correctness part. Again, how many segments of these we can have? Like, okay, in each of this segment, we are allowing. Okay, so for the ES instance, if the edit distance was really less than k, right? In this case, what is happening? Previously, I was starting the LCE query over here, and here I'm just moving even down. Like I'm even moving more forward. So I'm not going to say in the ES instance, I'm not going to say no. Right? ES instance stays yes. And the question is like, can I, if the number of edits is too much over k squared, can I say no? Can I say yes even in that situation? Like what is happening here due to synchronization? Previously, wherever my LCE query, errors were only coming from these segments. Instead of being exact, I was allowing k errors, right? Now, because of this shift, there could be some errors due to the shift as well because of the synchronization. But how much that error could be? Like at every point I get stuck, I can move like k diagonals here and there, right? So you might add a shift error of order of k whenever you're getting stuck. And how many times will you get stuck? You will get stuck at most k times. So the shift errors will be about order of k squared. So yes, there will be substitution errors of about k squared, and there will be shift errors, but shift errors is also about order of k squared. So within a constant factor, you are fine. So if you're saying yes, the edit distance has to be below k squared. So the correctness is fine. Now the question is, how does it help us to reduce the time complexity because of this synchronization? Well, so for here, if you look at here, right, like you have synchronized, you are in the same position at y, right? But still, if you're thinking in this way, there might be k LCE queries that you have to ask, right? From the same position y, but still there could be k LCE queries that you have to ask. Now, the nice trick over here is to exploit periodicity in strings. The periodicity in the strings is saying, if I can slide along these multiple diagonals here, then there must be some structure in your string, right? Like if I'm looking at x here, sliding along multiple diagonals means I'm using this diagonal, I'm sliding, this is matching over here. This diagonal, if I'm sliding, this is matching over here. This diagonal, if I'm sliding, this is matching over here. Right, which means my string y is periodic. And that also means like, yes, like my string x is also periodic. So if it indeed happens, there are multiple diagonals through which I can slide, both x and y must be periodic. Okay, So this is the insight that we had. And another interesting observation that we saw that, well, yes, like if there are multiple diagonals that we want to consider, that is multiple LC queries, then it's the strings are periodic. So maybe I don't check each of these diagonals separately, but I just check for periodicity instead. And another observation that we had, that when the periodicity breaks, then there could be only one diagonal where you won't see an error. It's possible there is one diagonal where you won't see an error, but in all other diagonals, you will see an error. Okay, so that means all those other diagonals you can discard, and then you are left with just one LC query. So that's the main idea. Just to show you a little bit more of that same concept of periodicity. So your X is periodic. If X is matching over multiple diagonals, then Y is periodic as well. Okay, so there could be many diagonals where it can match. But now if you see a mismatch anywhere here, like it was periodic, but it was certainly there is a mismatch over here, then as you try to compare the other diagonals, they will also start making mistakes over on that point. Okay, so which means in all diagonals, you will find an error when the periodicity breaks. So basically this is saying that you don't really have to check for every K diagonals, you just check for periodicity. And when the periodicity breaks, there could be at most one diagonal. And why there could be at most one diagonal? Essentially, it could happen that this diagonal where the periodicity broke, it also broke here, it also broke here. So only this diagonal survived. It didn't make a mistake, but everywhere else there will be a mistake. Okay. So just check for periodicity, and this can be done using sampling of n over k sampling rate. And once the periodicity breaks, spend order k time to find the surviving diagonal. And on the surviving diagonal, ask the LC query. So overall, how many LC queries then you ask? Like for every synchronization step here, you did the periodicity check, right? Somewhere periodicity broke. You know that everything, except for one diagonal here, everything had error. Forget about those diagonals. Then you just have one surviving diagonal. On that, you ask a LC query. So every time you're stuck, you are asking one LC query. You can get stuck at most k times. For every time you're getting stuck, you're spending order of k time, right? So overall, you have k square, and this global sampling rate is giving you n over k. So that's kind of the basic idea of how you get n over k plus k square time, and you can distinguish k versus k square. Questions?
How are you checking if a diagonal breaks?
How are you checking? So you check for periodicity. Okay, so you're checking with sampling. That you're sampling over here, and you're sampling over the same positions over here. You're checking whether the periodicity is maintained. At some point, periodicity, if you find a violation here, that this is violating, at this point, you go to the X, all the diagonals, you spend order k time matching. Like, okay, so the main diagonal, match it here, here. For diagonal 1, diagonal 2, diagonal 3, you will spend order k time. But there is just now one position.
Also, the number of queries is
Order k, right? So that's why like you need this order k space around every time you get stuck. But you are now making one LC query per such position. So overall, it gives you order of k square. Okay, so it's not just about k versus k squared. You can extend it to k versus any k prime. And in that case, like you will still be doing a synchronization, but you won't be doing a synchronization over like all k diagonals. You will consider the diagonals in band, and you will be doing synchronization only in band. Yeah. So like you will come here. Previously, you were saying, hey, I will do synchronization like I have 1, 1, 1 here. I will do synchronization here like this. Now here I get stuck. 2, 2, 2 here. Like I will do synchronization like this. But if this picture should make it clear. Like here, I'm not doing synchronization overall. I'm doing synchronization here in the white band. In this cream band, I'm doing a synchronization. In this white band, I'm doing the synchronization and so on. So this is just to reduce the amount of shift error. Because as you are doing synchronization, you are paying shift errors. You're paying errors in insertion deletions. So if you're not doing not synchronizing too completely, you are reducing the amount of shift error. And then you can increase the sample rate to reduce the number of errors per LC query. Okay, so by doing that, you can handle K versus K prime, where K prime is less than K squared. Okay, before I end, I just want to say a little bit about okay, so these are all about approximate computation. What about exact computation? Because in most of the cases in practical applications, you want to know exact. Okay, so in this scenario, at least you have, if you think about this kind of model where you have many DNA sequences, but you are allowed, you are anyway going to sequence them and you are going to store them. So if you think about, okay, so as each of the DNA sequences are coming, I'm pre-processing them. I'm spending linear time per string to pre-process. And after that, I spend linear time pre-processing the string on the left-hand side, string on the right-hand side. But then the queries could be pairwise queries. Okay, so you have the string A, string B, have the pre-processed information for each of them separately. In the Landau-Wishkin algorithms, the pre-processing needs to consider both strings together. Okay, so here I'm saying the pre-process the strings separately. After this pre-processing phase, you ask pairwise queries, and you have to really return these pairwise queries first. In this kind of pre-processing model, in fact, what you can show that in order of K squared time, you can give exact answer. Overall, if you are thinking about theoretical results, there are theoretical results which shows that any polynomial pre-processing time is not going to break the strong exponential time hypothesis. You will still won't be able to get any sub-quadratic exact algorithm. But in practice, if K is small, then indeed pre-processing really helps. With a query time of order of K squared, you can return exact answer. And this is a very simple algorithm that we had. Well, in Landau and Wishkin, you really need these two strings to bring the to pre-process using suffix tree. What instead you can do, you can pre-process the strings using, and you can store some rolling hash functions. Okay, so once you store the rolling hash functions, these LC queries, instead of having constant time per LC query, you can compare log n such rolling hash functions, and you can compute these LC queries in order of log n time. But in this case, the pre-processing becomes separate. You separately pre-process X, separately pre-process Y. You spend log n times per LC query, and then you just run Landau-Wishkin. When you are running Landau-Wishkin, if the pre-processing phase is done, you are spending at most K squared time. Okay, so with K squared log n, you can return exact answer. And obviously, there are many open questions here, how you can reduce. Is this K squared time necessary? Or a more practical model will be where you have your database where you have pre-processed all the sequences, but now a new sequence comes which is not pre-processed. So it's one sequence is pre-processed, the other is not, and you want to compute the distances first. So there could be other models which are more practical. Anyway, so these are open questions. There could be many more open questions in this area. Sublinear time, you saw what is the state? We at least know pretty well for non-adaptive algorithms, but for adaptive algorithms, the scenario is still not quite satisfactory. Dynamic algorithms, in fact, nothing is known in dynamic algorithms for edit distance beyond some trivial bounds. So everything is open for dynamic algorithms. There has been a lot of work on approximation and near neighbor search. Nothing is known for edit distance, again, beyond some trivial bounds. Approximation algorithms, a lot of work has been done, but still we do not know whether it's possible, for example, to get a 1 plus epsilon approximation in sub-quadratic time. And obviously, when you're stuck with worst cases, beyond worst cases, definitely an area where you can explore put your energy in. There are some results there as well, known for edit distance computation, but still there are big gaps between lower bounds and upper bounds. And generalization for other sequences, we're talking about edit distance, is really not required to talk about edit distance. You can think about any other similarity measures. You can think about distances from models rather than distances from a sequence, which is known as, and this model is specified by some formal language, you call it language edit distance. And all of these sequence problems actually have this Lifshitz or continuity property. Like if you perturb your input sequences slightly, then your output is not going to change much. Okay, so that property is exploited. Even if you think about Landau-Wishkin, like we're saying, hey, how far can I go with 0? Then what should be the values in the nearby cells in the dynamic program? It can be just +1 or 0, right? So the difference cannot be too much. So that's the continuity property. So almost all algorithms, when you have better algorithms than trivial, whatever you can get by dynamic programming or exhaustive search, that needs to exploit this Lifshitz property. Graph distances. And there is another interesting value to consider is like computing over compressed data. So if you're thinking about sublinear time algorithms, if your data is compressible, suppose you compress your data, and then over the compressed data, you run a linear time algorithm. But still over the, considering the input size, like uncompressed input size, it will be sublinear. So what can you do in that scenario? It could be either lossless compression or lossy compression. We have some results for lossless compression. We don't have anything for lossy compression. So that's another area which is very interesting for sublinear time algorithm design. Okay, so I think I'm done. I just want to say about the TCS Women workshop that will happen in Stock, where Shivanki will be on the panel, right? And Jessica will be one of our Rising Star speakers, and Urpita had been a Rising Star speaker for TCS Women. So as Lisa mentioned, like I was so influenced in my career by coming to Women in Theory. It's like for us to saying thank you. Like this is like, this Women in Theory has been so influential in many of like career of women researchers. So this TCS Women is trying to bring more women students to Stock and Fox. If you haven't heard about it, like we provide scholarships, travel scholarships to women students. So even if you do not have a paper, you can apply for TCS Women Scholarship and come to Stock. We organize Rising Star workshop, like Rising Stars, workshop for graduating students. So that's where Urpita attended, and Jessica will be there. We have panels and other things. We are also looking for volunteer, but if well, it's a great opportunity for many of you. If you want to attend Fox and Stock, you can look out for the scholarships. Okay, thank you.
We have a particularly short break, so we're not going to take any questions, but then, there will be banquet tonight. If you have questions, please ask Barna then. So the plan now is it's already 3:05, 3:15, we plan to have a group picture just outside. So don't go far. And before this talk, I sent out a link for the second day survey. So after the panel, please just fill it in. It's actually very, very important for us to have your feedback. So you stay near here. Yeah, thanks. Yeah, 2 hours.